Okay, hello all. My name is Elaheh Hayati from University of Arizona. I'm a graduate student and working with my great advisor, Peter Behrouzi. So I'm working on I actually want to estimate the dark matter halo properties of the Milky Way and Andromeda using applied machine learning. So the focus of my work is to determine the Milky Way's dark matter halo properties, including mass, concentration, spin axis, and assembly history of the dark matter halo. Okay, so there's a question: have people done this research before? So I should say yes, people have done this research before, but just for measuring the mass and not other properties of the Milky Way, and using dynamical tracers. So actually measuring the halo mass accurately is really important because it's important for direct dark matter searches, since a small change in halo mass can result in order of magnitude of difference in the number of dark matter particles that we have. And also measuring the mass of the Milky Way and Andromeda is also important for interpreting challenges to Lambda CDM. And one of these challenges is too big to fail problem, in which the Milky Way and the larger local group have too few dense satellites compared to Lambda CDM simulation. So having smaller or larger mass influence the type of satellites we get. So we are proposing a new way with the most accurate halo constraint for both the Milky Way and Andromeda. Okay, so there have been many techniques to estimate the Milky Way and Andromeda dark matter halo mass, and these techniques may be divided into two categories. So based on whether or not they involve priors from Lambda CDM simulation, and the techniques that do not involve the Lambda CDM simulation must all of them make assumption about the dynamical state of the system, and it is very common assume dynamical equilibrium. On the right, we can see a summary of the past Milky Way halo mass measurements from the Wang paper, and on the x-axis we have M200, which is the enclose the area with 200 times of the background density, and the dotted vertical lines indicate a range of 3 decks. And y-axis are different methods, and the ones that I showed with yellow are based on dynamical equilibrium, and the ones with purple are based on Lambda CDM simulation, and the black one had both methods on it. So this plot is the summary for the Andromeda halo mass measurements, and similar to the previous figure, different methods give a wide range of mass estimates, which gives plus minus 5 dex uncertainty for the Andromeda. So the methods that are based on dynamical equilibrium have a general strength in that information from multiple tracers can be self-consistently combined. But the negative point is that the system is actually not in the dynamical equilibrium. And this assumption causes systematic offset from the true mass that are difficult to model. For example, the passage of the Large Magellanic Cloud into the Milky Way disrupted the velocity and density disruption of stars along its orbit. Also, mass is continuously accreting on the outer skirt of the Milky Way's halo, and objects that orbit close to the halo's virial radius have experienced a gravitational potential that changed significantly over an orbital period. So here there's a video from Nico Gravito, and so it's showing how the passage of the Large Magellanic Clouds into the Milky Way can disrupt the velocity and density disruption of the stars distribution. And okay. Okay, then the measurements that are based on London-Studium simulation, they share a general strength in that they do not assume dynamical equilibrium, and at the same time, the negative point of them is that with each additional observational constraint, it becomes harder to find halos that match all the constraints simultaneously. So these techniques share a general weakness in that they are limited to how many different observational constraints can be combined at once without introducing further assumptions. Which also limits their overall constraining power. Okay, now, if the general mapping between the available sets of observables and halo mass were known, then it would be straightforward to determine the Milky Way's and Andromeda's halo mass by inserting the appropriate observations. So we are searching for observables that correlate with halo mass, and the one that can be really accessible are the motions of the satellites, and so with Gaia mission we have very precise proper motions and distances to many satellites around the Milky Way. And so we can use these as dynamical tracers of the halo mass. So now we know that satellites have distances and velocities that both increase with the mass of the host halo. So, and it means their specific angular moment also scales with a power of halo mass. So as I said, we are searching for a relation between observables and halo mass of central halos. So we have some input that has information about the halo mass encoded in it, and then by doing some analysis on our input, which here just the average of all angular momentum of satellite halos, we will get the mass of central halos as our output. So this plot is actually showing the simplest analysis method by averaging the angular momentum of satellite halos. And the y-axis is showing the average of angular momenta of the satellite halos. The red line is the power law, which has the slope of 2/3, and the green line that I showed here is I just wanted to show that the formula that we had on the previous page is correct. So the average angular momentum of 1.17 give the mass of 10 to 12 of halo. So now if we want to do something more complex and not just the average, but the full distribution of satellite angular momenta, then here is when my approach comes in. So I propose to find a general mapping between the observables and halo mass using deep neural network. So my approach has some strong points. First, arbitrary numbers of observations can be self-consistently combined. So my approach has greater constraining power. Than existing simulation-based techniques. Second, my approach makes no assumption about dynamical states of the system and is just based on Londosidium prior. So it has fewer systematic errors. I can also use the full information from simulations instead of being limited to only those halos that's most similar to the Milky Way and Andromeda. And also it can measure other halo properties beyond mass. So for my input simulation, I use the very small multi-dot prank simulation. So these are the primarily results of my work. So on the left, we train a neural network to predict halo masses from the a specific angular momentum of the 10 most luminous satellites, and then on the right, we apply the neural network on 30 most luminous satellites, and it yields to more accurate central halo. As we can see, we have much less outliers. And the red line shows the one-to-one relation for a perfect predictor. And the yellow error bars shows the standard deviation of the predicted halo mass as a function of actual halo mass. And the yellow dots with error bars shows the median and 1 sigma range of the predicted halo mass. So here I just add one environmental information, which is here is the tidal force information. And by adding this tidal force, we can see that most of the outlier were gone, and we got a better result. So for future works, I'm going to do further optimizing the neural networks by adding more environmental information, measuring other halo properties, including concentration, spin axis, and halo assembly history, and also cross-training using halos from high-resolution hydrodynamical simulations. And for the summary, up here you can see all the previous works that I show for the Milky Way, and then I added actually my work down here, which is a new constraint, and we can see it's tighter than all other work that we have here, and it's about 0.15 dex. Then by adding environmental information, which is here tidal force, the uncertainty is even less, and is about 0.11 dex. I think it's, yeah, that's it. Thank you.
All right, questions? Please say your full name.
Excuse me, this is Peter Bruzzi. Thanks for a very nice talk. I just wanted to clarify this last point is a predicted constraint as opposed to a constraint that's been run on observations.
So Christian Jespersen, so this constraint that you're quoting here in the end, I'm assuming that that's just like on kind of like perfect data from the simulation. How does that how does the tightness of that constraint change if you impose some kind of selection effect? And or have you tried that?
Oh, you mean, for example, so you mean trying on not just dark matter only simulation?
No, more like if I, like let's say I go out and I actually observe M31, and I miss a couple of the satellite galaxies, and so my total angular momentum will be kind of off, and there will be uncertainties in the total angular momentum. How much does that propagate through to your constraint?
I think I didn't get your question correctly.
Okay, we can take it afterwards as well.
Sorry.
Hey, thanks for the talk. It's a related question. So you said you have a constraint that is tighter than the others. Probably you said that and I missed it, but I was wondering how you estimate the uncertainty that you get, and how robust is this uncertainty estimation that you're providing?
Okay. So I actually shouldn't do this. I actually should just have just two dotted line showing the the uncertainty is about 0.15 dex. This is that I'm showing here. It actually should be like the two dotted line, not this yellow, line that I had. But
I think Mike might be asking a different question. If you go back to the slide showing the predicted versus actual halo masses. Yeah, that one. So it's basically just saying that if you look at a test set that you've never seen before, never trained on before, then how well can you predict the halo masses of the test set that you haven't seen? And so that's what all these blue dots are showing as test halos from the very small multi-dark Planck blocks. that the neural network has not been trained on before.
Alexander Ciprianovich, so I guess suggestion for future work, I don't know if you're related to this question. One thing that you could probably also test doing is adding, the network should also train to get you an uncertainty and a mean, and then you get an extra point. My question is, I don't know if you had time to do this already, or have you thought about it? So you've been showing these two cool plots with like 30 satellites and 10, I think. And have you tried removing even more satellites to see when your results really get really, really bad? Just so that we can like think about like, okay, for Milky Way, maybe we can measure a lot, but if we want to apply this in real data to any other more distant galaxy, how many satellites do we want to be able to observe and still be confident in the predictions? It's fine if you haven't tried it already, but if you haven't tried, it would be a fun thing to see, like when does the model break down?
I understand that, but I think if I remove more data, I cannot get a more precise result.
Yeah, but because like with 10, it's still, I mean, yes, the spread I see it's larger, but it still kind of works. So just a fun thing to test is like, when does it become completely crazy? Yeah. Like we don't want to trust it at all.
Yeah, that's right.
Yeah. So just a comment for future, I guess.
Any questions?
Actually, just following up on that, you probably said this, but I think I missed it. What information do you need about these N satellites for example, following up on that question, we now have 100 systems which have on average 3.5 satellites. So if you could get some measurement, but you may or may not have the right data on those objects. So could you just remind us what data you need for the satellites?
So the position and velocity, so because we're gonna, put our input are the angular momentum of the satellites. So
and so probably regular redshift space is not good enough. Here you're thinking about using more detailed information.
Exactly.
Right, so if no more questions, let's thank Elaheh again. And all right, so that's the end of the first session in the morning, and I guess we'll reconvene here at 11.